Today, we're diving into something pretty incredible, how machine learning is starting to decode what you might call the dark matter of the molecular world. All of this is based on a fantastic 2025 review by Hong, Yi, and Tang that looks at the intersection of AI and mass spectrometry. So let's get right into it.
Okay, so try to wrap your head around this. Imagine trying to understand the universe when 95% of all matter is just invisible. Well, that's almost exactly the problem we have in chemistry. It's estimated that a staggering 95% of small molecules, the very building blocks of biology and medicine, are completely unidentified. This huge unknown chemical space is what we call molecular dark matter.
So that leads to the big question, right? How in the world do we shine a light on this invisible world? How can artificial intelligence actually help us map, identify, and really understand these millions of unknown molecules? Well, in this explainer, we're going to walk through exactly how that's beginning to happen.
We're going to tackle this in 6 parts. First, we'll really define the problem of molecular dark matter. Then, we'll look at how we actually teach machines the language of chemistry. From there, we'll cover some advanced learning strategies, see how AI can predict unseen data, and then how it solves the much harder inverse problem. And finally, we'll look ahead at the scientific revolution this is all kicking off.
All right, let's kick things off with Section 1, the molecular dark matter. Before we get into the AI, we really need to understand the fundamental challenge here that machine learning is now perfectly poised to solve.
So the key piece of tech here is something called mass spectroscopy, or MS. The easiest way to think about it is as an incredibly precise scale for molecules. But just knowing a molecule's weight isn't enough to know what it is. That's where tandem mass spectroscopy, or MS/MS, comes in. If MS is like weighing a complete Lego model, MS/MS is like smashing that model into pieces and then weighing every single piece. This pattern of broken pieces, that creates a unique structural fingerprint.
And here's the kicker. For decades, the only way to identify a molecule was to match its fingerprint to a known one in a reference library. Think of it like a chemical Shazam. But what happens if the song isn't in the database? You get nothing, no match. Building these libraries is super slow and really expensive, and they can't possibly contain every molecule out there. This is what we call the library bottleneck, and it's the reason why potentially life-saving drugs or dangerous environmental toxins can go completely undetected.
So, how do we break through that bottleneck? Well, that brings us to Section 2, Teaching Machines Chemistry. This is all about translating the language of molecules into a language that an AI can actually understand.
To teach a machine about a molecule, we first have to represent it in numbers, and there are a few main ways to do this. We can use descriptors, which are just simple numerical features like how many atoms it has. We can use fingerprints, which are basically long strings of ones and zeros indicating if certain chemical structures are present. We can even use text strings like smiles, which are a line of text that describes the structure. Or, and this is the most powerful way, we can represent molecules as graphs, where the atoms are the nodes and the bonds are the edges connecting them.
And what's really cool about this slide is how it takes those abstract ideas and makes them totally concrete. You can see the exact same molecule, but represented in all these different ways, as a set of numbers, a line of text, a binary fingerprint, and a 3D model. Each language gives the AI a totally different perspective on the molecule structure.
Now, when we use those molecular graphs, really cool models like message-passing neural networks, or MPNNs, come into play. And the process is just brilliantly intuitive. Information literally spreads across the graph. First, in the message-passing step, each atom gathers information from its direct neighbors, kind of like gossip. Then, in the node updating step, each atom updates its own state based on the gossip it just heard. You do this a few times, and then a final readout function pulls all this local information together into a single, really rich representation of the entire molecule. It's pretty elegant.
Okay, so representing the input molecule, that's only half the battle. We also have to represent the output, that MS/MS fingerprint. And we can do this in 2 main ways. We can turn it into a binned vector, which is perfect for models like convolutional neural networks, or we can represent it as a peak list, just a sequence of mass and intensity pairs, which is a really natural fit for sequence models like transformers. So you see, how we represent the data fundamentally shapes the kind of AI we can actually build.
Okay, let's move on to Section 3, Advanced Learning Strategies. The thing is, we have pretty limited high-quality data in this field, so we need some really clever ways to train our models.
The key here is just making the absolute most of the data we have. With self-supervised learning, we can pre-train models on these massive databases of unlabeled molecules just to learn the general rules of chemistry.
Then, with transfer learning, we can take that pre-trained knowledge and fine-tune it on a much smaller, more specific dataset. And with multitask learning, we train a single model to predict several different properties at once, which forces it to learn a much more robust and generalizable understanding of the molecule.
And now we get to the first really big application. Section 4, predicting the unseen. This is what's called the forward problem. Basically, if we already know a molecule's structure, can we predict what its experimental fingerprint is going to look like?
And there are really two main schools of thought here. On one hand, you have end-to-end models, like MassFormer. These try to learn a direct mapping from the molecular structure straight to the final spectrum. On the other hand, you have two-step methods, like CFMID. These try to explicitly model the physics by first predicting which fragments a molecule will break into and then predicting how intense each of those fragments will be. Now, beyond just the MS fingerprint, we can also predict other properties to get more evidence for what our molecule is. We can predict its retention time, which is basically a measure of its stickiness as it moves through a chromatography column. We can also predict its collision cross-section, or CCS, which tells us about its 3D size and shape. Every single one of these predictions adds another layer of confidence to our identification.
And all of that brings us to the ultimate challenge. Section 5, the inverse problem. This is so much harder. Now, we have the experimental data, we have the fingerprint, but what molecule did it actually come from?
The very first step is just figuring out the chemical formula. You know, how many carbons, hydrogens, oxygens, and so on. Two strategies really dominate here. The top-down approach, used by a tool called Sirius, is kind of like the funnel on the left. It starts with all the possible formulas that could match the molecule's weight and then uses the fragmentation data to rank them from most to least likely. The bottom-up approach, used by a tool called Buddy, does the exact opposite. It builds up potential formulas directly from the small fragments it sees in the spectrum, like the pyramid on the right.
And this slide really shows you just how sophisticated these tools have become. Sirius actually builds these complex fragmentation trees to explain how every single peak in the spectrum could have possibly been formed. Buddy, on the other hand, uses powerful machine-learned ranking models and even calculates a false discovery rate, which gives researchers real statistical confidence in their predictions. But look, even if we know the formula, there's an even deeper puzzle: fragment ion annotation. This is the challenge of linking every single peak in the spectrum back to the exact piece of the molecule that created it. This is a crucial and still largely unsolved problem where machine learning is just now beginning to make a real impact. So this all leads us to our final section. Section 6, the next scientific revolution. Where is all of this incredible technology actually heading?
Well, there are still some major frontiers to cross. Generalization is a huge one, just making sure that a model trained on data from one lab's instrument actually works on data from a different one. Multimodal learning is another big frontier. This means effectively weaving together all the different data types we have, the fingerprint, the retention time, the collision cross-section, into one super powerful predictive model.
But the ultimate goal, the holy grail of this entire field, is ab initio prediction. It's the ability to determine a molecule's complete 3D structure directly from its spectral data alone, with zero need to match it to any library, anywhere. This is the key that will finally unlock the molecular dark matter for good. And that really just leaves us with a final thought to chew on. If we could identify any molecule in any sample, from our own bodies, from our food, from our environment, what problems could we finally solve? From discovering new medicines to diagnosing diseases earlier than ever before, the possibilities, well, they're truly revolutionary.